A single teaspoon of neutron star material weighs as much as a mountain. These cosmic corpses left behind by supernova represent a state of matter so extreme it shatters our basic understanding of physics. By the end of this journey, you will understand how these objects bend the very laws of nature beyond recognition. We will uncover what happens when atoms are crushed out of existence, and explore if the core is made of a strange soup of free quarks. How does it feel to know the universe can twist reality so completely? That staggering weight begins with a stellar death more violent than anything we can comprehend. A star, many times more massive than our Sun, spends its life in a delicate balance, with the outward push of nuclear fusion holding back the inward crush of gravity. But when its fuel finally runs out, that balance shatters in an instant. Gravity wins. The star's core, no longer supported by fusion, collapses at speeds approaching a quarter of the speed of light. This creates a shockwave of unimaginable force that rips the rest of the star apart in a supernova explosion, briefly outshining an entire galaxy and seeding the cosmos with the elements that make up our world. And at the heart of that cataclysm, the true miracle occurs. All that remains is the collapsed core, a city-sized sphere crammed with more mass than our Sun. This is the neutron star. The pressure is so immense that atoms themselves are obliterated. Electrons are literally slammed into protons, and they merge, transforming into neutrons and ghostly particles called neutrinos in a frantic process scientists call neutronization. In less than a second, the very identity of matter is rewritten. The resulting object is unbelievably small, unbelievably dense, and unbelievably hot, as described by astrophysicist Jocelyn Bell Burnell, who first discovered the radio pulses from these spinning corpses. This initial compression is merely the opening act, setting the stage for the truly bizarre physics that govern the neutron star's interior. That initial collapse creates a substance so alien it defies common sense. Think of the space inside a normal atom. If you enlarged a hydrogen atom to the size of a football stadium, its nucleus would be a mere pea on the center of the field, with the electron a distant speck in the stands. A neutron star annihilates that emptiness completely. Every last bit of space is squeezed out. The stadium, the field, the seats, all of it is crushed down into that single, impossibly dense pea. The immense gravitational pressure, equivalent to hundreds of millions of Earth atmospheres, forces electrons and protons to merge, transforming into neutrons. The result is a city-sized object made almost entirely of neutrons, packed shoulder to shoulder with no room to breathe. To grasp this density, picture compressing every single person on Earth, all 8 billion of us, into the volume of a single sugar cube. That is the reality inside a neutron star. This bizarre substance is called neutron degenerate matter, and it behaves like nothing you have ever touched. It is not a solid, a liquid, or a gas. It is a quantum sea, a continuous nuclear fluid where the normal rules of atomic behavior break down. At these unimaginable densities, a quantum rule called the Pauli exclusion principle becomes the dominant force. This principle says that no two identical particles can exist in the same place with the same energy. It is this rule, not atomic bonds, that creates a final, desperate pressure holding the star up against its own weight. The neutrons are so densely packed that they have nowhere left to go, creating a degenerate matter that resists further collapse with unimaginable strength. This is matter stripped to its absolute essence, a state of existence forged only in the heart of a stellar cataclysm. How could such an environment not produce phenomena that seem like magic? This quantum sea is a realm where intuition fails completely. We are used to matter behaving in predictable ways, governed by temperature and pressure. But inside a neutron star, a different set of laws takes over. The bizarre rules of quantum mechanics pushed into overdrive. Here, The primary force holding the entire star up against its own crushing weight is not heat or fire, but a purely quantum phenomenon known as degenerate pressure. This pressure has nothing to do with temperature. It is a fundamental refusal of particles to be squeezed into the same state. The neutrons, packed unimaginably tight, have their individual quantum identities overlapping and blending. They are fermions, a class of particles that strictly obey the Pauli exclusion principle. This principle is the ultimate cosmic rule of personal space. It dictates that no two identical neutrons can occupy the exact same quantum state, the same energy level and position. With gravity trying to compress them into an ever smaller volume, the neutrons simply have nowhere left to go. Their resistance to this final violation creates an immense, unstoppable outward push. It is this quantum standoff, this rebellion against being forced into the same identity, that prevents the neutron star from collapsing into a black hole. The entire structure exists in a precarious equilibrium, a fragile truce between the inward crush of gravity and the outward, quantum mechanical refusal of neutrons to be squeezed any further. This understanding was built on the genius of physicists like Subrahmanyan Chandrasekhar, who first calculated that for white dwarf stars, a similar electron degeneracy pressure had a limit. His work showed us that when gravity wins, matter must transform. Neutron stars are the next chapter in that story, where degeneracy pressure is taken to an even more extreme conclusion. In this environment, the line between the atomic and the astronomical completely vanishes. The behavior of a single subatomic particle directly dictates the fate of an object with the mass of a star. What other secrets are hiding within this quantum standoff? And what happens when even this incredible force finally fails? But even this quantum sea has a shore, a solid boundary where matter takes on yet another impossible form. This is the neutron star crust, a crystalline skin forged under pressures that make the center of our planet feel like a soft vacuum. Here, gravity's immense squeeze does not immediately pulverize every atom. Instead, it performs a bizarre alchemy. The nuclei of atoms, usually stable structures of protons and neutrons, are forced to absorb an overwhelming flood of neutrons. They become grotesquely overweight, transforming into exotic, ultra-heavy isotopes that could never exist on Earth. Imagine a lead atom, but swollen to twice its normal mass, its identity stretched to a breaking point. These super-heavy nuclei do not float freely. Under the crushing pressure, they lock into a rigid, perfect grid, a crystalline lattice of atomic giants. This structure is so strong it qualifies as the hardest solid in the entire universe. And yet, it is punctuated by imperfections. The crust is not perfectly smooth. It has mountains, but on a neutron star, a mountain is not a colossal peak reaching for the sky. It is a tiny ripple, a deformation no taller than a few centimeters. Do not let that modest height fool you. Because the crust is so unimaginably dense, that centimeter-high bump contains more mass than Mount Everest. When the neutron star spins, these minuscule mountains create a wobble in its rotation. According to Einstein's theory of relativity, any accelerating mass can ripple the fabric of spacetime itself. These tiny crustal deformations, therefore, can generate faint, detectable gravitational waves, sending whispers of the star's structure across the cosmos. The crust is the ultimate barrier, a solid shield protecting the universe from the even stranger reality within. It is matter's final, organized stand before descending into the pure neutron chaos of the core. What could possibly lie beneath such an unyielding surface? Descend past that unyielding crust, and you enter a realm where solidity gives way to a slippery, impossible sea. This is the inner crust, a transitional zone where the rules of matter become even more fluid. The grid of super-heavy nuclei begins to stretch out, creating more space between these atomic islands. In these gaps, a strange rain begins to fall, Individual neutrons, no longer bound to any nucleus, literally drip out into the void, forming a bizarre ocean that defies all our experiences with liquids. This is not a normal fluid. It is a neutron superfluid, a state of matter that flows with zero friction, zero viscosity, and zero resistance. Imagine a whirlpool that, once set in motion, would spin forever without ever slowing down. This happens because the free neutrons, under these extreme conditions, do not behave as individual particles. They pair up, locking into a coordinated quantum dance, and move as a single, coherent entity. It is as if an entire ocean decided to act as one single, impossibly connected wave. This superfluid property is not just a theoretical curiosity. It has dramatic, observable consequences for the entire star. The superfluid in the inner crust can rotate at a different speed than the star's solid, magnetic outer crust. Think of it like an egg, where the liquid yolk inside can spin independently of the hard shell on the outside. This differential rotation builds up stress. Occasionally, this stress is released in a sudden, violent event that astronomers can detect from light years away. The star literally glitches, its rotation rate suddenly jumping in a fraction of a second. These spin-up events are the direct signature of the superfluid inside, transferring its momentum to the solid crust in a gigantic quantum hiccup. The study of this behavior bridges the vast gap between the atomic and the cosmic. Nobel laureate Anthony Leggett's work on terrestrial superfluidity in helium gave us a glimpse of these quantum rules. But in a neutron star, these effects are magnified to a stellar scale by unimaginable density and magnetic fields. This frictionless realm is matter in a state of perfect coordination, a dynamic and restless layer that governs the star's spin, its magnetic field, and even how it cools over billions of years. It is the final frontier before we plunge into the ultimate mystery, the very heart of the star where matter may cease to be matter at all. What bizarre substance could lie deeper than this perfect, frictionless fluid? And so we arrive at the final frontier, the very heart of the star where the known laws of physics begin to fray. This is the Core Enigma, a place where the neutrons themselves, unable to withstand the final crushing pressure, might shatter into their most fundamental components. We are no longer dealing with neutrons, but with a hypothetical substance known as quark matter. Picture a vast ocean where the very concept of a particle dissolves into a seething, primordial soup of free quarks and gluons. This is a quark-gluon plasma, a state of matter that has not existed widely since the first microseconds after the Big Bang. On Earth, we can only create fleeting specks of this plasma in colossal machines like the Large Hadron Collider, for tiny fractions of a second. But here, in the core of a neutron star, nature may have forged a stable, city-sized droplet of the early universe itself. This is matter stripped of all identity, reduced to its most basic ingredients. Another possibility is even stranger. The core might be filled with Hyperons. These are exotic particles that are like unstable, heavy cousins of the familiar protons and neutrons. They contain a type of quark not found in stable matter, known as the strange quark. Under the normal conditions of our world, Hyperons decay in a blink. But inside a neutron star, the pressure is so immense that it becomes energetically favorable for neutrons to transform into these strange particles, creating a hyperonic core that is stabilized by the very forces trying to crush it. The existence of either quark matter or hyperonic matter would challenge the very foundations of the standard model of particle physics, forcing us to rewrite our understanding of the strong nuclear force that binds the universe together. The true nature of the core is encoded in the neutron star's equation of state, a theoretical description of how matter behaves at these insane densities. If the core is made of free quarks, it could become a color superconductor, a substance that allows electric current to flow with literally zero resistance, but for the strong force instead of electromagnetism. This would be a state of matter even more perfect than the inner crust superfluid, twisting the laws of physics into unrecognizable shapes. The composition of the core remains one of the greatest unsolved puzzles in all of science, a mystery locked inside a cosmic vault spinning 1,000 times a second. What other impossible realities are waiting to be discovered when we finally learn to read the secrets hidden in these gravitational beacons? This magnetic ferocity finds its ultimate expression in a specific class of neutron star, the magnetar. If an ordinary neutron star is a cosmic wonder, a magnetar is that wonder twisted into a weapon of pure energy. Its magnetic field is not merely strong, it is an entity in itself, 1,000,000,000,000 times more powerful than Earth's field and 1,000 times stronger than that of a typical neutron star. To grasp this power, consider what would happen if you were to approach one. Long before you even got close, the magnetic field would dismantle you on an atomic level. It would warp the electron clouds surrounding every atom in your body, stretching and tearing them until the very chemistry that constitutes your form simply ceased to function. You would be pulled apart not by gravity, but by magnetism itself. The source of this phenomenal power lies in the star's turbulent birth. During the core collapse of the supernova, the star's original magnetic field, already intense, becomes compressed and wound up by the rapidly spinning newborn neutron star. It is like taking a humble electromagnet and crushing it down to the size of a city while spinning it 1,000 times a second. The result is a magnetic dynamo of almost incomprehensible intensity. This field is not a passive feature. It is an active, restless force that grips the entire star. It exerts such immense stress on the solid iron crust that it can literally twist it, causing fractures known as starquakes. These are not gentle tremors. A starquake on a magnetar releases more energy in a split second than our sun will emit in 100,000 years. This energy erupts into space as a blinding flash of X-rays and gamma rays, a beacon of violence that can be detected from clear across the Milky Way. In 2004, a magnetar 50,000 light-years away released a flare that, for 1/10 of a second, delivered more energy to Earth's upper atmosphere than a solar flare, despite being halfway across the galaxy. The magnetic field is a colossal battery, storing energy that, when it suddenly rearranges itself, can produce a flare that outshines every star in its host galaxy combined. This magnetic dominance dictates the star's entire life. It slows its spin, channels its cooling, and forces the degenerate matter within into strange, aligned structures. Magnetars show us the absolute upper limit of magnetic power in the cosmos, a fundamental force pushed to its breaking point. They are natural laboratories for physics that cannot be replicated anywhere else, revealing how matter behaves when not just crushed, but also utterly dominated by a field that can tear reality apart at the seams. This dizzying spin takes the neutron star's strangeness and launches it into the realm of pure relativity. Some of these stellar corpses whirl around hundreds of times every single second. At that speed, a point on the equator would be moving at a significant fraction of the speed of light. This ferocious rotation does more than just make the star spin, it actively reshapes it. Immense centrifugal forces push material outward at the equator, squeezing the entire sphere into the shape of a flattened ball, an oblate spheroid. It is a planet-sized object contorted by its own impossible velocity. But the consequences go far deeper than mere shape. According to Einstein's theory of general relativity, such intense gravity and speed warp the fabric of spacetime itself. This creates a gravitational time dilation effect. If you could place a clock on the surface of a neutron star, you would see its ticks slow down compared to a clock far out in empty space. Time itself flows at a different rate in that extreme environment. This warping is not just a theoretical idea. It is a measurable part of the star's identity, especially when that spin is channeled into a beacon. When a neutron star's powerful magnetic field is misaligned with its rotation axis, it can transform into a pulsar. Think of it as a cosmic lighthouse. Beams of intense radiation shoot out from the magnetic poles, and as the star spins, these beams sweep across the sky. From a distance, if one of those beams happens to point toward Earth, we see a regular, repeating pulse of energy, a blink that can be more precise than any atomic clock we can build. This precision turns pulsars into extraordinary tools for science. Astronomers use their steady pulses to test the predictions of general relativity with incredible accuracy, to map the structure of the Milky Way, and even to hunt for the faint ripples in spacetime known as gravitational waves. Yet this precise clock is slowly winding down. The energy powering those brilliant beams and the intense magnetic fields is siphoned directly from the star's rotation. Over millions of years, this loss of spin energy causes the pulsar to gradually slow, its pulses becoming farther and farther apart. This spin down is not just a simple slowing, it is a key part of the star's life cycle, influencing the internal dynamics of the superfluid core and the stability of its solid crust. The relativistic spin of a neutron star does not merely exist within spacetime. It actively bends and molds the cosmic fabric around it, creating a natural laboratory where the universe tests its own most fundamental laws. That same gravity that forges its impossible interior also creates a surface from which nothing can truly escape. The pull on the surface of a neutron star is so powerful that to break free, to achieve escape velocity, you would need to be launched at a significant fraction of the speed of light. We are not talking about the fiery thrust of a rocket, but a velocity approaching half of the universal speed limit itself. This is not a hill to climb, but a vertical, gravitational cliff face. This overwhelming force does not just affect matter, it warps the very light leaving the star. Photons, particles of light, must expend tremendous energy to climb out of this deep gravitational well. As they struggle against the star's pull, they lose energy, their wavelength stretching out toward the red end of the spectrum in a phenomenon called gravitational redshift. The light we eventually see is a tired, diminished version of what was originally emitted, a direct signature of the immense gravity at work. To even contemplate standing on such a surface is a thought experiment in instant annihilation. The force, billions of times stronger than Earth's gravity, would act on every single atom in your body simultaneously. You would not fall. You would be pulled into a thin film, a smear of subatomic particles merging seamlessly with the star's own nuclear material in a fraction of a nanosecond. This gravitational dominance shapes even the star's atmosphere, a wispy layer of ionized gas only millimeters thick. Here, individual atoms are stripped of their electrons and held in place by a brutal combination of magnetic forces and the sheer, inescapable weight of gravity. This creates a closed system, a cosmic roach motel where matter checks in but it never, ever checks out. Any gas or dust drifting too close is captured, accelerated to incredible speeds, and slammed onto the surface, its mass and energy becoming a permanent part of the star's dense structure. This relentless accretion of matter is how neutron stars often reveal themselves to us, pulling material from a companion star in a binary system and creating brilliant, energetic displays. How does this process of cosmic consumption look from the outside, and what happens when a neutron star begins to feed? This devouring act begins with a cosmic theft. In a binary system, a neutron star's immense gravity can reach out and strip the outer layers from a companion star. This stolen gas does not fall straight down. Instead, it forms a vast, spinning disk of superheated material, an accretion disk that spirals inward like water circling a drain. As the gas is pulled deeper into the star's gravitational grip, it accelerates to incredible speeds, gaining enormous kinetic energy. All that violent motion is converted into heat, raising the temperature of the gas to millions of degrees. Long before it even touches the surface, this infalling matter glows with a fierce, searing light, emitting a torrent of high-energy X-rays that we can detect across interstellar space. The final impact is a continuous, unimaginable explosion. But sometimes, that impact triggers something even more spectacular. As the stolen hydrogen and helium pile onto the neutron star's surface, the pressure and temperature at the base of this new layer become so extreme that nuclear fusion ignites in a runaway chain reaction. In a single furious flash, the entire accumulated layer of fuel fuses into heavier elements in less than a second. This is a Type I X-ray burst, a thermonuclear firestorm that can outshine 100,000 suns, a brilliant, repeating flash that signals the star's surface is burning. This process of accretion does more than just feed the star, it can reanimate it. The infalling matter carries angular momentum, a rotational energy that it transfers to the neutron star like a cosmic whip. This can spin the star up to incredible speeds, reactivating it as a pulsar, its lighthouse beams sweeping the galaxy once more. Yet this feast is not without its dangers. Every ounce of accreted matter adds to the star's total mass, pushing it closer to its ultimate fate. There is a precise limit, a tipping point known as the Tolman-Oppenheimer-Volkoff limit. If the neutron star accretes enough material to cross this threshold, the quantum pressure of the neutrons can no longer hold back gravity. In a final, silent collapse, the entire structure would implode, vanishing from sight and leaving behind a black hole. These binary systems are therefore cosmic balancing acts, a delicate dance between feeding and self-destruction. And in their violent interactions, they serve as forges for the universe's heaviest elements. The rapid fusion in X-ray bursts and the intense neutron flux during accretion can create atoms like gold, platinum, and uranium, which are then scattered into space by the explosions or outflows. The very gold in a wedding ring may have been forged in such a cataclysmic feeding frenzy, a permanent record of a star's final, transformative meal. This relentless feeding and spinning cannot last forever, for every neutron star is born a seething inferno and destined to become a cosmic cinder. Its thermal evolution, the story of how it cools, is a silent narrative written in neutrinos and X-rays. Immediately after the supernova, the newborn star's temperature can soar beyond 1 billion degrees Kelvin, a heat so profound it rivals the first moments of the universe. But this furnace cannot contain its own energy. The primary escape route is through the most ghostly of particles, the neutrino. These elusive, nearly massless entities are born in the star's crushing core, and because they barely interact with normal matter, they can flee directly through the solid crust and into space, carrying immense amounts of energy with them. This neutrino emission acts as a cosmic air conditioning system, bleeding the star of its ferocious birth heat at a staggering rate. For the first million years or so, this is how the star cools, its internal temperature plummeting even while its surface still glows fiercely. The exact speed of this cooling, however, is not a simple process. It is a direct probe into the star's deepest secrets. If the core is filled with exotic matter like free quarks or hyperons, these particles can create additional pathways for neutrino production, accelerating the cooling in a way we could potentially detect. A star cooling faster than our models predict might be a signal that we have found a quark star, an object even more fundamental than a neutron star. Conversely, if the core contains a superfluid of paired neutrons, this can actually suppress certain neutrino processes, acting like a thermal blanket and slowing the star's cooling. It is as if we are listening to the star's heartbeat through its temperature, and the rhythm tells us what it is made of. As the neutrino flood subsides, a second, slower cooling phase takes over. The star's surface begins to radiate its remaining heat away as photons, from visible light down to X-rays. Astronomers use powerful space telescopes to detect this faint X-ray glow. using it to estimate the star's true age and peer into its internal dynamics. Each temperature measurement is a data point on a cooling curve, a line on a graph that can confirm or shatter our theories about the strong nuclear force and the very nature of matter. This gradual loss of heat reveals the final, quiet fate of these titans. They are not just bending matter, but our most fundamental concepts of temperature and energy, showing us that even in the cold of space, the slow whisper of cooling can tell the most explosive stories. Even the quietest death of a neutron star can be undone by a violent reunion. When two of these dense corpses become locked in a gravitational dance, their fate is sealed. They spiral inward over millions of years, losing energy in the form of ripples in spacetime, until they finally merge in a cataclysm that outshines a billion suns. This collision is so powerful it briefly outshines all the stars in its host galaxy combined, and the gravitational waves it produces, like those detected from event GW170817, shake the very fabric of the universe. For the first time, we not only heard the cosmic thunder of such an event, but also saw its brilliant afterglow. A new era of multi-messenger astronomy where we can listen to the universe's most violent events, and then turn our telescopes to watch them unfold. The energy released in these few seconds is greater than our Sun will produce across its entire 10 billion-year lifetime. But the true miracle is not the raw power. It is the creation that happens within it. The debris ejected from this collision is a superheated, neutron-rich cloud, a cosmic forge for the universe's heaviest elements. Here, a frantic process called the Rapid Neutron Capture Process, or the R process, takes place. Atomic nuclei are bombarded by a flood of free neutrons, growing heavier and heavier in an instant, forging elements like gold, platinum, and uranium, substances that could never be born in the heart of an ordinary star. The distinctive glow of this radioactive debris, a kilonova, is our direct evidence of this cosmic alchemy. The gold in a wedding ring or the platinum in a catalytic converter was almost certainly forged in such a violent stellar collision billions of years ago. We are literally made from the remnants of these ancient cosmic catastrophes. During the merger itself, conditions become even more extreme than inside a solitary neutron star. For a fleeting moment, matter is subjected to such immense pressures and temperatures that the neutrons themselves may completely dissolve, creating a fleeting, city-sized droplet of free quarks, a state of matter that has not existed since the first moments after the Big Bang. Alternatively, if the combined mass is too great, the entire merger remnant can immediately collapse into a newborn black hole, a silent end to a spectacularly loud event. The aftermath then scatters these newly minted heavy elements across interstellar space, seeding nebulae that will one day form new stars, planets, and perhaps even life. These violent unions are not just destructive ends, they are creative beginnings, fundamental to the chemical richness of our universe. They bend matter to its absolute limit, and in doing so, they create the very building blocks of our world. This incredible precision transforms a collapsed star into a tool of unparalleled accuracy. A pulsar's pulse is so regular that its rhythm can be predicted thousands of years into the future, a metronome ticking with more stability than the finest atomic clocks we can build. This reliability comes from the neutron star's ultimate rigidity. Its solid crust and quantum-dominated interior form a structure so unyielding that nothing can disrupt its spin except over cosmic timescales. It is a gyroscope forged from degenerate matter, spinning in the vacuum of space with almost no friction to slow it down. The mechanism creating the pulse itself is a spectacle of raw power. The star's immense magnetic field, trillions of times stronger than Earth's, acts like a colossal particle accelerator. It rips electrons and other charged particles from the star's surface, whipping them along curved magnetic field lines to velocities approaching the speed of light. This violent acceleration forces the particles to emit radiation across the entire spectrum, from radio waves to deadly gamma rays, focused into two narrow, opposing beams that shoot out from the magnetic poles. If the star's rotation axis is misaligned with its magnetic axis, these beams sweep through space like the blazing arms of a cosmic lighthouse. We only detect a pulse if one of those beams periodically flashes across our line of sight. This simple geometry creates one of the most useful phenomena in the universe. Astronomers use these predictable flashes as navigation beacons to chart the solar system, to test the subtle predictions of Einstein's general relativity with exquisite precision, and to probe the thin gas between the stars. The very first planets ever discovered outside our solar system were not found around a sun-like star, but in the grim vicinity of a pulsar. This revealed that planetary systems can form from the ashes of stellar cataclysm, surviving in environments of intense radiation. The ultimate application of this timing may be the detection of the universe's faintest hum. By monitoring networks of these cosmic clocks across the galaxy, scientists are creating a pulsar timing array. The goal is to sense the minute distortions in spacetime caused by passing low-frequency gravitational waves, ripples from the mergers of supermassive black holes. A pulsar's steady beat is more than a curiosity. It is a direct signal from a realm where matter is bent into a perfect timekeeper, allowing us to listen to the quietest symphonies of the cosmos. The ultimate fate of a neutron star is written in a single, profound relationship known as the equation of state. This is not a simple formula, but the very rulebook that dictates how matter behaves when crushed beyond all recognition. It describes the intimate connection between the pressure trying to hold the star up and the density trying to pull it down. This fundamental law determines everything about the star, from its maximum possible mass to its final radius. Think of it as the star's genetic code, defining its physical identity against the relentless will of gravity. Different theories about the star's core predict different equations of state. If the core is a sea of free quarks, the equation of state becomes soft, meaning matter compresses more easily, leading to a smaller, denser star. If the core is made only of neutrons resisting further collapse, the equation of state is stiff, resulting in a larger, more robust object. The difference is a matter of cosmic life and death. A stiffer equation of state allows a neutron star to support more mass before collapsing into a black hole. A softer one means it will surrender to gravity at a much lower mass, vanishing from the visible universe. This is why astronomers are so desperate to measure the size and mass of these objects. Every observation is a test, a real-world experiment pitting our theories against the universe itself. The echoes from colliding neutron stars, the precise timing of pulsar spins, and the faint X-ray glow from their surfaces all provide crucial data points. Each new constraint helps us eliminate impossible equations of state, homing in on the one true law that governs matter at its most extreme. This makes neutron stars our only reliable laboratories for studying forces that we could never hope to recreate on Earth. They are the key that unlocks the behavior of the strong nuclear force, the very glue that holds every atomic nucleus in our world together. By deciphering this code, we are not just learning about distant stars, we are uncovering the fundamental rules that bind reality itself. We cannot see a neutron star directly, but we can read the stories they broadcast across the cosmos. Each type of signal they send requires a different kind of cosmic ear to listen. X-ray telescopes, like the Chandra Observatory and the Neutron Star Interior Composition Explorer, or NICER, are our eyes for extreme heat. They map the incredible temperatures on a neutron star's surface, pinpointing hotspots that glow with X-rays created by magnetic fields and infalling matter. By carefully measuring the energy and timing of these X-rays, scientists can perform a kind of cosmic cartography, estimating the star's size and the properties of its crushing gravity. This data provides a direct line into the mysterious equation of state, telling us whether the star is relatively large and squishy or small and ultra-dense. It is like trying to understand the composition of a distant, metal ball by studying the precise spectrum of light it emits as it cools. The information is subtle, but it is the closest we can get to physically touching these objects from light years away. Meanwhile, radio telescopes listen for the metronomic heartbeat of pulsars. The steady, predictable pulses of radio waves allow for timing so precise it can detect a slow-down equivalent to a single second over 10 million years. This precision is not just for keeping time. It reveals the star's slightest wobbles and hiccups, the glitches that betray the turbulent superfluid sloshing within its interior. By tracking how these pulses are delayed as they pass through the interstellar medium, astronomers can even use pulsars to map the ghostly magnetic fields that stretch between the stars. How else can we sense an object that warps the very fabric of reality itself? That answer came with the first detection of gravitational waves from a neutron star collision. When two of these objects spiral together, they do not just flash with light, they shake the universe. Observatories like LIGO and Virgo felt the spacetime ripples from event GW 170817, a moment that opened an entirely new sense for exploring the cosmos. These waves carry a direct imprint of the star's masses and how they deformed each other just before merging, offering a pure, unadulterated glimpse into the behavior of matter at the extreme. The true power, however, lies in combining all these senses at once. A multi-messenger approach where a single event is observed with gravitational waves, X-rays, gamma rays, and radio waves, builds a complete picture no single method could provide. It is like identifying an animal in the dark by listening to its roar, feeling its footsteps, and then finally seeing its shadow in a flash of lightning. We are even building detectors to catch the neutrinos that would stream from a nearby supernova, ghostly particles that would give us a live feed from the heart of a collapsing stellar core. These combined observations have decoded the language of neutron star activity, translating glitches into stories of superfluid vortices, and X-ray bursts into tales of nuclear fire on an ultradense surface. Our most advanced technologies are the keys that unlock these cosmic vaults, allowing us to test our wildest theories about the fundamental nature of reality from the safety of our own pale blue dot. These cosmic engines are not endpoints, but essential recyclers in the galactic machine. Every neutron star begins its life by scattering the raw materials of creation. The supernova that forges it blasts the outer layers of the progenitor star across light years, seeding interstellar clouds with oxygen, carbon, and iron. This enriched gas becomes the building blocks for the next generation of stars, planets, and ultimately, life itself. The neutron star left behind continues this work over eons. Its intense magnetic field and radiation carve into surrounding nebulae, creating vast, glowing structures known as pulsar wind nebulae. These energetic bubbles can compress nearby gas, triggering the gravitational collapse that births new stars. In other circumstances, that same radiation can blast a cloud apart, evaporating it and halting star formation before it even begins. A single neutron star becomes a sculptor of its local cosmos, its influence reaching far beyond its own unimaginable density. This dynamic interaction is a fundamental part of the galactic ecosystem, a feedback loop where the death of one star directly dictates the birth of others. Their role becomes even more profound when they are paired. In a binary system, a neutron star can slowly siphon material from its companion, a process that not only powers brilliant X-ray emissions, but also dramatically alters the evolution of the other star. This stellar theft can strip a star down to its core, prematurely ending its life or changing its ultimate fate. In the most extreme cases, this accretion of mass can push the neutron star over its stability limit, causing it to collapse into a black hole, or lead to a cataclysmic merger that forges the universe's heaviest elements. The gold in a ring and the uranium that powers nuclear reactors were almost certainly forged in the debris of such a neutron star collision, a kilonova that scattered these rare metals across the galaxy. This is the grand cosmic cycle made visible. The most massive stars live fast and die violently, creating neutron stars that then pollute the interstellar medium with the elements necessary for rocky planets and biology. These dense remnants lock away a tremendous amount of mass, but through their winds, their radiation, and their spectacular mergers, they give back something far more valuable: the chemical diversity that allows for complexity to arise. They are both creators and destroyers, catalysts and crucibles. To see a neutron star as merely a dense curiosity is to miss its true significance. It is a vital organ in the living body of a galaxy, a key player in the endless loop of stellar death and rebirth that makes a universe like ours even possible. How does this grand perspective change our view of our own place within this magnificent, interconnected cosmic web? This is the frontier where our most elegant theories of physics begin to crack under the pressure. We have two magnificent pillars supporting modern science: general relativity and quantum mechanics, and inside a neutron star, they wage a silent war. Relativity masterfully describes the immense, smooth curvature of spacetime created by the star's gravity. Quantum mechanics governs the frantic, probabilistic dance of the subatomic particles packed within. The problem is, these two rulebooks were written for entirely different domains, and in the core of a neutron star, their jurisdictions violently overlap. We lack a single, unified theory of quantum gravity to tell us what truly happens when the fabric of spacetime itself is bent by densities where quantum uncertainty reigns supreme. This is not a minor gap. It is a fundamental chasm in our understanding of reality. The behavior of matter here is dictated by quantum chromodynamics, the theory of the strong nuclear force that binds quarks together. But applying it is notoriously difficult. At these densities, the calculations become what physicists call non-perturbative. You cannot simply add up small, manageable interactions. You are faced with the full, chaotic, and overwhelming strength of the strong force all at once. It is like trying to predict the precise pattern of a raging hurricane by studying a single, gentle breeze. The complexity is so profound it defies our current mathematical tools. This is why the true nature of the core remains a mystery. Is it a soup of free quarks or a color superconductor? Our theories allow for these spectacular possibilities, but without a direct window into the core, they remain brilliant speculations, haunting the edges of established science. Even observations are now challenging the models we do have. Astronomers have found neutron stars like Pulsar J0740+6620, which tips the scales at over 2.0 solar masses. This is a weight that should crush certain soft equations of state, forcing matter to collapse into a black hole. The fact that these heavyweights exist tells us that neutron star matter must be stiffer, more resistant to collapse than some of our best predictions allow. They are cosmic outliers that break our rules, forcing us to go back to the drawing board. Then there are the mysterious fast radio bursts, incredibly brief, intensely powerful blasts of radio waves from distant galaxies. While some appear to originate from the dramatic Starquakes of Magnetars, their sheer energy and variety suggest there might be other, even more exotic engines at work, perhaps involving these dense objects in ways we have not yet conceived. Each unexplained flash is a potential clue, a signal from the dark that our map of physics is still missing whole continents. This constant confrontation with the unknown is not a failure of science, it is its very engine. The limits exposed by neutron stars are already inspiring radical new ideas, from modifications to Einstein's theory of gravity to entirely new particles and forces beyond the standard model. These objects do not just bend matter, they stress-test the foundational principles of our universe, revealing where our knowledge ends and the next great discovery must begin. These stellar corpses are more than just cosmic curiosities. They are our most advanced laboratories. The extreme conditions within and around a neutron star create a natural testing ground for the laws of physics, performing experiments at energy scales we could never hope to achieve in a particle collider on Earth. The most precise of these tests comes from the steady, predictable pulse of a pulsar. When a pulsar orbits another dense object, like a white dwarf or another neutron star, its clock-like rhythm becomes a probe for spacetime itself. As the pulses travel through the curved space around its companion, their timing is minutely affected. One such effect is the Shapiro time delay, where a pulse is slightly slowed as it climbs out of the gravitational well of the companion star. The measured delay perfectly matches the predictions of Einstein's general relativity, confirming that gravity indeed warps the flow of time, a phenomenon we can only verify with such accuracy out here in the cosmos. These binary pulsar systems were also the first to provide indirect evidence for gravitational waves. As the two stars orbit, they lose energy by rippling spacetime, causing their orbits to slowly shrink. The rate of this orbital decay, detected through exquisitely precise timing of the pulses, matches Einstein's predictions with astonishing fidelity. It is a direct, real-world demonstration of a consequence of general relativity that was once thought to be virtually unmeasurable. The star's interior acts as a crucible for the strong nuclear force, the powerful yet short-range glue that binds atomic nuclei. Here, matter is compressed to densities similar to that of a giant atomic nucleus, but one the size of a city. By studying how a neutron star responds to this pressure, its overall size and the maximum mass it can support, we are essentially studying the properties of nuclear matter on a colossal scale. The equation of state is our translation key, turning astronomical observations into fundamental insights about the force that holds all visible matter together. This probe extends even to the most elusive particles. Neutrinos, those ghostly travelers, are central to a neutron star's birth and its long, slow cooling. The rate at which a star cools tells us about the processes happening deep within its core. Processes that produce floods of these particles. An unexpectedly fast cooling star might be a sign of exotic particles or new neutrino interactions at work, offering a window into physics beyond the standard model. And in the realm of a magnetar, physics becomes even stranger. Magnetic fields trillions of times stronger than any we can generate can alter the very nature of the quantum vacuum. Theorists predict effects like vacuum birefringence, where the empty space around the star acts like a crystal, bending X-ray photons in two different directions depending on their polarization. Some models even suggest that these intense fields can spontaneously create matter and antimatter from nothingness, a process known as pair production, sparking the magnetar's powerful flares. These objects also serve as potential traps for dark matter. As a neutron star moves through the galaxy, its immense gravity could pull in dark matter particles, which would then collide and annihilate inside the core, potentially providing a detectable heat source that slows the star's cooling. Each glitch in a pulsar's spin, each flicker in its X-ray glow, and each new gravitational wave signal is a piece of data from an experiment run on a cosmic scale. They bend matter not just into strange shapes, but into instruments of discovery, revealing the deepest laws of the universe from within their own impossibly dense hearts. An atom's identity, defined by the number of protons in its nucleus, is completely erased within a neutron star. We classify the world around us using the periodic table, a tidy grid of elements from hydrogen to uranium, but inside this cosmic forge, that entire system becomes meaningless. The immense pressure dissolves the familiar architecture of an atom, protons and electrons are forced to merge, transforming into neutrons in a process that obliterates the very concept of an elemental signature. What remains is not a collection of different atoms, but a continuous, seething ocean of nuclear material, a substance where the idea of carbon or iron or gold has no place. The interior is composed almost entirely of neutrons, with only a tiny fraction of free protons and electrons swimming in the mix. This is matter stripped of its chemical identity, reduced to its most fundamental nuclear components. Even on the surface, where conditions are slightly less extreme, no atom survives intact. The ferocious gravity and density rip electrons away from their nuclei, creating a sea of ionized gas. Bare atomic nuclei, stripped of their electron clouds, become embedded within a degenerate electron gas, a quantum mechanical fluid that behaves nothing like the electrons orbiting a normal atom. This radical alteration changes how matter interacts with light. In a laboratory on Earth, we can identify elements by the unique fingerprints of light they emit or absorb, their spectral lines. But on a neutron star, these spectral lines are dramatically shifted, smeared, or entirely absent. The extreme magnetic fields and pressures distort the energy levels within any remaining atoms so severely that their light signatures are blurred into oblivion. This redefinition extends to the violent environment of an accretion disk. When a neutron star pulls gas from a companion star, that incoming matter is rapidly processed. The stolen hydrogen and helium are accelerated, heated, and compressed, triggering a frenzy of nuclear reactions that quickly transmute the material into heavier elements before it ever reaches the surface. The entire system operates on nuclear timescales, governed by the strong force, not the comparatively gentle rules of chemistry. Neutron stars push matter beyond the periodic table, into a realm where the very idea of an element is a quaint memory. They show us a universe where the building blocks of our world are not permanent, but are merely temporary arrangements in the face of overwhelming force. Deep within the inner crust, matter organizes itself into forms stranger than any science fiction. Here, the distinction between individual atomic nuclei begins to dissolve completely, forced by pressures that defy comprehension. This gives rise to a bizarre state of matter physicists call nuclear pasta. It is not a liquid or a solid in any normal sense, but a series of complex shapes that form as nuclei are squeezed together until they merge into continuous, extended structures. The driving force behind this cosmic sculpting is a fundamental competition between two of nature's most powerful influences: the strong nuclear force, which binds protons and neutrons together, desperately tries to clump matter into larger chunks. Opposing it is the Coulomb force, the electromagnetic repulsion between positively charged protons, which tries to tear those chunks apart. Under the neutron star's immense weight, this battle reaches a stalemate, and matter must find the most energy-efficient way to exist. The resulting shapes are a physicist's pantry. At slightly lower densities, nuclei stretch into long, thin rods that pack together like a bundle of spaghetti. As the pressure increases, these rods might fuse sideways into flat sheets, resembling cosmic lasagna. Under even greater force, the sheets can perforate, forming a honeycomb of tubes, or invert into a Swiss cheese-like matrix of bubbles. Each configuration represents a different phase, a different way for matter to endure the unendurable. This nuclear pasta is not merely a curiosity, it is likely the strongest material in the entire universe. The bonds within these structures are the powerful nuclear force itself, making them astronomically more resilient than any steel or diamond. The mechanical strength of this cosmic material is so profound that the crust can support mountains only centimeters high that nonetheless contain the mass of entire Himalayan ranges. The stress building up in these incredibly rigid layers is thought to be a primary cause of starquakes, those sudden, catastrophic rearrangements of the crust that release more energy than 1 billion atomic bombs. When a sheet of nuclear pasta cracks or a tube of spaghetti suddenly snaps, it can trigger a glitch in the star's spin and unleash a flare of radiation, a direct signal of this internal struggle echoing across light years. How can we possibly study a substance that exists only under such impossible conditions? Scientists rely on massive computer simulations, using supercomputers to model the interactions of millions of particles as they are crushed together, virtually recreating the forces that sculpt these shapes. By comparing the predicted effects of nuclear pasta on a star's behavior, like its specific glitch patterns or how it cools, with actual observations from telescopes, we can look for the unique signatures of lasagna deep within a pulsar's crust. This peculiar state of matter reveals a universe of stunning complexity, even in its most extreme environments. It shows us that matter, when pushed to its absolute limit, does not simply become a uniform mush, but can self-organize into intricate, ordered forms, adding a final, deliciously bizarre layer to the way neutron stars bend the laws of physics beyond all recognition. The same gravity that forges nuclear pasta might also be trapping the universe's most mysterious substance. Dark matter, the invisible scaffolding of galaxies, could be flowing through a neutron star's core, caught in an unseen gravitational web. While this matter does not emit or reflect light, its gravitational pull is felt across the cosmos. A solitary neutron star, drifting through a dense cloud of dark matter, would act like a cosmic fishing net. The star's immense gravity would pull in these hypothetical particles, which would then collide with the dense nuclear matter inside, losing energy and becoming trapped. Over millions of years, a significant amount of dark matter could accumulate at the very center of the star, creating a dense, dark nucleus within the already bizarre core. This accumulation is not a passive process. It could fundamentally alter the star's life cycle. If certain theories are correct, these trapped dark matter particles could annihilate upon contact with each other, converting their mass directly into pure energy. This energy release would inject heat into the star's core, acting like a hidden furnace deep within the cooling stellar corpse. For an old, cold neutron star, this could mean the difference between a frozen cinder and an object that remains unexpectedly warm for billions of years. Astronomers searching for especially warm neutron stars might, in fact, be looking at the indirect glow of annihilating dark matter. In even more dramatic scenarios, a runaway accumulation of dark matter could trigger a catastrophic collapse. If too much mass builds up in the core too quickly, it could push the star over its stability limit, causing it to implode into a black hole in a silent, dark-induced cataclysm. Alternatively, some models suggest the rapid energy release from dark matter annihilation could rip the star apart in a unique kind of supernova, an explosion powered not by fusion, but by the invisible universe. This makes neutron stars natural, pre-built detectors, operating on a scale and sensitivity far beyond anything we can construct on Earth. They are constantly performing this experiment, using their own immense density as the target. By carefully observing the temperature and spin of isolated neutron stars, we can look for anomalies that betray this dark interaction. A star that cools too slowly, or whose rotation behaves in an unexpected way, could be giving us our first real clues to the nature of dark matter. This transforms these luminous objects into bridges between the seen and the unseen, bending our search for the hidden 95% of the universe toward the most extreme environments we know. The next generation of cosmic observatories is already on the drawing board, ready to pry open these stellar vaults with tools of unimaginable precision. The European Space Agency's Athena X-ray Observatory will act as a powerful space-based microscope, trained directly on the searing surfaces of neutron stars. It will map their hotspots and measure their tiny sizes with unprecedented accuracy, finally pinning down the elusive equation of state that dictates their very existence. On the ground, the Square Kilometre Array, a radio telescope with the sensitivity to detect an airport radar on a planet dozens of light years away, will listen to the synchronized beats of thousands of pulsars at once. This vast network of cosmic clocks will create a galactic-scale gravitational wave detector, sensing the low-frequency hum of orbiting supermassive black holes and providing a new way to watch for the spacetime ripples from distant neutron star mergers. These missions will not work in isolation. When a gravitational wave observatory with improved sensitivity, like the future Cosmic Explorer, feels the telltale shudder of a neutron star collision, Athena and the Square Kilometer Array will swivel to capture the aftermath in X-rays and radio waves. This multi-messenger approach will build a complete, three-dimensional picture of these cataclysmic events, from the initial inspiral to the creation of heavy elements in the expanding Kilonova cloud. For the first time, we will watch the forging of gold in real time, but our vision will extend even deeper, into the very moment of a neutron star's violent birth. A new generation of neutrino telescopes, buried deep in Antarctic ice or under the Mediterranean Sea, lies in wait for the next nearby supernova in our galaxy. These detectors will catch the flood of ghostly neutrinos that carries away 99% of the collapsing star's energy, providing a live data stream from the heart of the cataclysm as a new neutron star is forged. This would be the ultimate inside look at the creation of one of the universe's most extreme objects. Meanwhile, the mysteries of the interior are also being attacked from another angle, through sheer computational force. Scientists are using machine learning and the world's most powerful supercomputers to simulate the chaotic dance of a neutron star merger, tracking billions of particles as they collide, explode, and form exotic nuclear pasta. These virtual laboratories allow us to test thousands of different equations of state against the torrent of new observational data, homing in on the one true law of matter at nuclear density. The collective power of these missions and technologies aims directly at the grandest unanswered questions. What is the true nature of the core? Is it a quark soup, a Hyperon fluid, or something even stranger? How strong can a magnetic field truly become before it fundamentally alters the vacuum of space? Each new glitch, each new gravitational wave, and each new temperature reading brings us closer to answers that will inevitably lead to new, even more profound mysteries. The future of neutron star research is not just about collecting data. It is about continuing a conversation with the universe, one that constantly challenges our perception of reality itself. That same cosmic laboratory also lives in our classrooms and our culture. Neutron stars have a unique power to ignite curiosity far beyond the halls of academia. Their staggering statistics, a teaspoon weighing 1 billion tons, a mountain only centimeters high, are not just abstract facts. They are tangible entry points into the fundamental laws of physics, making the bizarre rules of quantum mechanics and relativity accessible and exciting. Educators use these extreme objects as dramatic illustrations, turning a dense stellar corpse into a story that makes students ask, what else is possible? This direct line from cosmic wonder to classroom inquiry inspires a new generation of astronomers, engineers, and dreamers, proving that the universe's greatest mysteries are its most effective teachers. That inspiration ripples outward into our shared culture. Science fiction authors weave tales of spacecraft navigating pulsar fields, while artists try to capture the eerie glow of an accretion disk or the impossible geometry of a star wrapped in gravity's lens. The very name, neutron star, carries a certain weight in our collective imagination, a symbol of ultimate power and mystery. This cultural reflection is more than just entertainment. It is a testament to humanity's enduring need to explore the unknown, to find stories in the stars that help us understand our own place in the cosmos. The study of these objects demonstrates a beautiful truth. That curiosity-driven research, the pure desire to know, often leads to the most profound innovations. The technology developed to listen for pulsar signals or to model nuclear pasta indirectly advances computing and data analysis for everyone. By bending our cultural narratives, by challenging us to think bigger and stranger, neutron stars do more than just transform matter. They reshape our minds, fostering the critical thinking and boundless imagination that will be essential for the next great leap in our journey among the stars. Neutron stars stand as monumental proof that the universe operates on a scale of wonder far beyond our everyday experience. These stellar remnants do not merely exist, they actively defy the rules, crushing atoms into oblivion, orchestrating quantum dances on a cosmic stage, and perhaps even cooking up a primordial soup of free quarks in their cores. From their cataclysmic births to their precise pulsar beats and their role as forges for galactic gold, they are relentless engines of physical extremes. They bend gravity, stress the strong nuclear force, and warp spacetime itself, offering us a front-row seat to physics we could never recreate. They are a powerful reminder that reality, at its most fundamental level, is far stranger and more magnificent than we often allow ourselves to believe. This journey into their heart is more than a catalog of facts. It is an invitation to perpetual curiosity. If this exploration has reshaped your view of the cosmos, there are countless more mysteries waiting for us. Consider subscribing to continue this journey together, and share which aspect of these cosmic marvels captivated you most in the comments. The universe is an endless source of wonder, and our shared curiosity is the key to bending our minds around its infinite, breathtaking possibilities.